So, once you are done with your pizzas, feel free to have a seat. We will soonish get started. Hi, thank you all for coming. Welcome to the House of Ideas and Monads in a different light. So, you've all probably read a ton of monad tutorials and thought that maybe there's a way to do it better, or at least figure out why they are so hard. So, here's an idea for that, right? Thank you.
Yes, good evening everyone, thanks for coming. Yes, so here's an angel as a title, starts on goodness. Who am I? Yes, my name is Christian Tinker, sorry. I'm a master's student at Haskell, and I wrote my PhD thesis in Haskell. And disclaimer, I'm not an expert on monads. I use them, I think I know them pretty well, but if I get something wrong, please don't do it. So, the intention of this presentation is to, if you're a Haskell novice, or if you don't know what monad is, to give you pointers where to look at to better understand monads, and if you're a Haskell veteran, to give you some ideas how to maybe better explain monads to some newcomer who goes to you for help. So, by the way, by show of hands, please, I'd like to get an idea of how they know the monad. So, please raise your hands if you know what a monad is, if you're very familiar with it. Okay? If you don't, please raise your hands if you don't know what a monad is, or if you're very afraid of what a monad might be. Okay, good. Okay, about half. So I think Haskell has an image problem, and people think that Haskell is very complicated, and the reason that often comes up is that monads are difficult. What are monads? Nobody knows because they are complex and abstract and whatever. And what are monads? I don't know. Oh, Jesus, these functional programmers, mumbo jumbo, whatever. So yeah, and everybody feels they have to explain what a monad is. So there is this ever-increasing amount of monad tutorials. Everybody tries to write a monad tutorial, and they finally get it. Yes, this is how to explain it. Yes. And apparently I joined this line, but anyway. This, I think, leads to this. When people try to comprehend these ever-increasing amount of monad tutorials, always seeing something different, they usually give up and say, yeah, I Haskell, yeah, functional programming, I heard about that. So I think it should, the problem is that many of these tutorials start with definitions. They give you the definition of the monad type class and what the return is and bind and all these things. I don't know why they do this, because I don't think they tell you as much as a good example would. And we don't think in these definitions of like what the monad is, because it's a simple example. When you see a dog in the street, you don't think about the definition of the dog, but whatever that might be. You know it's a dog because you've seen dogs before, so you will recognize them. And I think this applies here. Another question might be, but do definitions help understand them even if you don't think in them? Well, I don't think because they do, because when you hear a definition, your mind has to instantiate it. You have to imagine examples which fit that definition. And essentially, this is harder than if you were just given some good examples, because then you wouldn't have to think about it. And actually, the definition of a monad is very complicated if you want to just imagine up examples. So, and by the way, I'm not saying that definitions are not important or that they are useless. I'm just saying that you should leave them after you're able to develop a good intuition of what a monad is with the example code. So yes. When somebody understands what a monad is, they usually, yes, the monad is a box, or it's a burrito, like it's yes, that's what a monad is. Okay, I have to tell the internet about this, and they write a tutorial or a description, and what they do is give you their own mental model, their own interpretation of this abstract concept, which is not the best thing to do, because then another interpretation gets thrown on the pile, another analogy gets thrown on the pile, and when someone tries to understand this, it's very difficult because layers get everything. So just to throw another one on the pile, here's my interpretation of the monad, but I think this is the image that I was missing when I was trying to understand what the monad is. So here is regular value, and you use return to put it in a computational context, and now it's in a monad, and then you can get it out sometimes, because if you're in a state monad or a state thread monad, you can use the run function of that monad to get out of that. If you're in a simple monad like list or maybe, then you can use pattern matching, and if you're in an IO monad, it's not possible. That's the risk, because you can actually get out of IO monad, but if you're just getting familiar with monads, you shouldn't want to. So yes, and now a list of confusing things about monads. And now, here's a fun game to play. It's the first point for a fun game to play. Ask a friend to point at an integer. Yeah, that's an integer. Okay. So where are you going to do this? Ask a friend to point at the formula. Yes, there it is. Okay, so now ask a friend to point at the mediator button, and I'm going to need some example code for that, because it's more I'm going to need you on my diagrams. Yes, because monads are like design patterns. So one important thing to keep in mind, even trying to understand what a monad is to not try to locate a separate thing to point at, because monads, much like design patterns, are structure, behavior, and a bunch of other things that you can't just simply put in a simple, object or something. You can't just point at it. You have to keep this in mind when trying to understand them. Yes, and now one of the best confusing things about monad is, why is return called return? So if you look at the definition for a monad, monad type class, because if you want to learn more, then you must have seen them, because that's what monad tutorials show you. Return has nothing to do with the return that is known from imperative languages. It literally has nothing to do with it. So I don't know why it's called that. Why is it called return? Yeah? Haskell history lesson. You can find this paper called a history of Haskell in basic class, and it's a 55-page long document, I think. It tells you about how Haskell evolved from its conception to 2007. And in this paper, you can find that it's called return. It calls return, but it cites a paper by Mark B. Jones, a system of constructor classes overloading an implicit higher order polymorphism. And in this paper, it's called result. It's not called return, it's called result. So I don't know why it got changed. Maybe it was called return earlier. Well, it cites another paper, and no, Philip Weidler, the essence of functional programming, it was called unit M and unit before. So I don't know why it was changed to that. It's actually confusing because return is, even in mathematics, a function have a return value. So it's just I don't know why they did that. I don't know. It's just like intentionally obfuscating the language for newcomers. So you have to keep this in mind. Forget things about other imperative languages, like names of things that shouldn't be called that anyway. Another confusing thing is the box envelope. The monad is a box. No, it's not. I think this is especially dangerous because when someone from Java or wherever else, I think in other languages they call them box values, comes and tries to understand monads and reads a monad as a box and you put valid values in them. Oh, I know, it's a boxed value. Yeah, that's what a monad must be. No, they aren't. So, and no, it's just another example of having an interpretation of the concept and thinking that's the right way to understand it. So try to forget about that. The monad is a box. It's not a box. The IO monad. It's another confusing monad. The name of IO is confusing because you think input-output. Well, it was introduced to implement input and output, but it's not just for that anymore. So it's okay that it's called IO because it has historical reasons, but actually IO is for anything that has a side effect. And what might be confusing is that all the other monads you can get out of, except for IO. You can, like I said, you can use unsafe pair from IO, but that is very dangerous if you don't know what you're doing, and it's only for implementing like high performance array libraries and such. So yes, and you should try to separate your logic from IO as much as possible. And there will be an example about it later. Yes, and the best one is the state monad because many monad tutorials cite state monad as state monad as an example. But where do I begin? The name of state monad is also already confusing. If you go to the wiki books of Understanding Monads and it has a page on state monad, it says the name of the state monad is a bit of a misnomer because it should be called state processor monad. It actually has a function in it. So if you try to imagine that state is a monad and it has a value in it, it has a function, and all the other monads you've seen before don't have a value in them. They don't have a function in them. They have a plain value in them usually. So why does this have a function? So what's up with this? I don't get it. When I first seen this, it was very confusing to me. But all the tutorials show you the definition, and you start reading it, and it's this, and it's not very helpful trying to understand this. Actually, what the state monad is the memory button on like a calculator. You get a single memory cell. It can be of any type. It can be a single integer. It can be a tuple. It can be a record. So you can put a bunch of stuff in it, and you can read it, write it, or apply a function to it, modify it in place. So that's all it does, and you can pass it along, and all this stuff is just plumbing. So in this definition, this is the secret. Why does it have two type parameters? The S is the type of the state you hide is a memory button, right? And the a changes, like as you pass through the do block, it changes value, like functions passing functions to each other. But state stays the same, and it's just all this line does is just hides the plumbing for passing this extra value of state, and it doesn't really tell you to study. Again, I think an example will be much more talkative. So, summary. Don't read definitions first. Don't be afraid to not understand things. I think is a good lesson to take away. And read examples. Names are confusing in Haskell, so never assume that because it's called something similar like in an imperative language, it does the same thing, because they don't. I don't know, like I said, I don't know what's computer. I always did not try to separate your code into, try to keep your function as pure as possible. I always think your C code. And be careful with trying to understand the state model. Now, we get to examples, which might be a lot more interesting than the first part of the presentation. And I think when trying to understand a concept like this, you should, in this order, try to find these kind of examples. Syntactical, which, I'll be honest, I realized this in the last minute, so I can't be the best name to choose for this. I mean the smallest kind of thing that the smallest elements, like how you can fit together the smallest bits of code that do something, just the syntax and the type system and how all the stuff works, figure that out. And then you find things that tell you how to write bigger bits of code that are still functional, like, I don't know, 10 line functions that's pretty long in Haskell. But something that does something useful but still small. And I want to show these two kinds of examples now. And the structural examples, I mean a complete program written in Haskell is very useful to look at. So to find examples of that, you can go to Hackage. Unfortunately, there is not a good repository of examples for the first two kind of what I know of. You can maybe go to Rosetta Code or something like that. But I think it would be good to maybe create a website of some sort where people can submit these kind of examples, syntactical and functional, how I call them, and for people to go there and just as a grab bag. I want to do this, how do I do this? I pull out an example of how to put together something. So this is an example for what I've called syntactical. So it's very simple, it's a function called f. It has a do block, and you can see in it that what this other thing does. You have a monadic value, this is a monad actually, and you can get value out of it. And now it's not monadic value, now it's a regular value, like an integer. It's an int. This, and it's a regular int. And then here you can apply a function to it, like multiplying by 2, and it's an int value, and if you return it, it makes it a monad value again. So type of return is int into int, list of int, and this whole thing will be a list of int. So the result of this program is a list of 2, 4, and 6, because when you try to get a value out of a list, actually it runs all the values of the list through X. And it applies the functions to all of them, and it returns a value. Actually, list comprehensions use this in the background. Yes, and this is an example for the IO monad. You use getLine, it gives you an IO string, and you can get out of IO. Yes, you can, because you're in an IO monad, so you can get out of it here. You get it out, put it in X. It's a regular string now, so you can just map to it, and put string line prints it out on the screen. It has a type of string to IO. You print it out, and the whole type of this expression is IO unit, which is, you can see there. So if you run this, if you can type something in, and it prints it out in uppercase. So yes, I think another useful educational exercise is to try to do this differently, or just tinker with it. So, a negative example, what happens, why does this not work? So another thing that's useful when learning something is to find out what you can do with them. So, for example, you can do this. Why can't you do this? Well, what does getLine return? It returns an IO string, and map works on regular strings or lists as it happens. So it's wrong type. So how do we fix this? We can use lift_m, which is a function for lifting regular functions to monadic functions in that it works. So another bad example. You use getLine to go to X, and then you try to map it to it, and oh yes, I can't. I don't even know what. Sorry. But what's? Oh yes, right. Yes. When you use getLine, you get a string, and then you map to it, and you get another string, and you try to unmap it to X. Now you can't do that because it's just a regular string. It's not an IO string. So if you return it, and then it's an IO value, so you can unpack it again. It's kind of stupid, but you actually, yes, you can write it simply, like a lot shorter. But the point of this is that you get a feel of the language. You can develop intuition without ever understanding, how the implementation of the monad works. I think it's like looking at the definition of a monad for learning what a monad is like looking at the definition of GCC to learn how to program C. You shouldn't know that necessarily. It's better to first understand it and then look at it, because you should know how it works, but you shouldn't start with that. So here is another example. This just takes basically a matrix of strings, and it returns indices of these string of various strings first occurring in these rows. So the point of this example is you can see that you can use pattern matching here. So actually, XS is a list of strings. So you can use zip with this, which just tags all of the string lists with numbers. So in this pair, you will have an integer and a list of strings, and then the 11th index finds the string if there is a string like that, and this returns a maybe value, and return makes it a list of maybe, but it doesn't actually matter what kind of one it is. The point is you can just pattern match it, and the best thing about the list monad is that when pattern matching fails, it just keeps the element. So if it doesn't find it, it just leaves the element out. So actually, you don't have anything in the third row, and the element index has nothing, and so it just keeps it, and it doesn't produce an error. Okay, state monad. This is the implementation of an insertion sort, and it's pretty. It's actually pretty terse. I think if you this is the code type. Is it known? Yes. This is the code for insertion sort I stole from Wikipedia, and I implemented this in Haskell. So if you look at this state monad, well, it's almost a literal transcription of this pseudocode to Haskell. You just for n, it is like a for loop. It iterates through these elements of the list, of this list, and applies them to all of them this function. this function. And modify is the function to modify the state of the state monad, and it applies this function to it, just gives it the value of e to j. Yes, the inner state of this monad is a pair now. LS is a list of the elements at the moment, and the other is just an index that this trailer code uses. So actually, this code could be written much simpler in Haskell, but the point was to demonstrate the usage of state. So here, for m, the underscore actually just applies this function to all the elements in this list and then shows the results, right? But modify changes the state of the state monad, so it all remembers it. And in the end, you use exec state to run this whole computation from the starting state of this. You have to provide that. So the first you have the regular list, and the index is 0, and it just runs the whole thing. And then you get out the first component of the pair, because that's the list. So actually I can show this in action. It's not very interesting, but still. So just slowly then you can sort list like 5, 6, 3, 2, and it's in the examples like this. Yes, so you see it works. Yes, yay. I really implemented a very simple function in a very complicated way. Anyways, the point is that I'm gonna put up this code somewhere on the meetup site, or I don't know. So if you want to study it, you can. And that's just it. And okay, next example. State thread monad. Yes, this is a very interesting monad, because actually you can you don't just have a single state. You can put things in. You have you can make as many variables as you want. So if you look at this line, j arrow new str graph 0 means to create a new state thread reference with a value of 0 and put it in j, and you can modify it using this function. It modifies the j reference using the function const I. So it means it actually just assigns it to it doesn't assign it, but it actually gives the value of I, and you can read it, modify it, and all these things. And actually, this uses a mutable vector. So this outer sort function gets a vector of integers, it pulls it, so it actually makes a mutable copy of it. It applies this integration sort function on it, which does its magic, and it freezes it, and then you get it back. And so basically, the state thread monad encapsulates mutable states inside the pure function, because if you look at it, the sort function has nothing like st or io in its signature, so it hides all of these things. And I think this is a very great example for monads, because it's much closer to the imperative style, so which is more familiar, and then you can condition imperative programmers to do imperative Haskell, and then you can get train them to now do normal Haskell. I think. Anyways, it's a bit ugly, because of you have to get out the value of the these references in the loop condition. So I'm just gonna leave that up to you to figure out if you want to. It's actually, you don't need to do this if you want to sort of. It's obviously just an example to show you these references. And you can use mutable vectors, like copy it, you use a function that you mutates it, freeze it, and everything is here. Okay, so yes. Speaking of this, the ST monad, to write my BSc thesis, I had to use a library called Juicy Pixels. Juicy Pixels is for reading and manipulating and writing images, and this is a function that gave me some headache. Does anyone know how this works? Show of hands, please. Do you know how this works, or have any idea what you need to do to get this to work? Okay, so yes, the signature is not very talkative, not very verbal. The multiple image, if you multiple image looks like this, it has a width and height, and this image that it has a ST vector in it. Still not very helpful. Actually, it took a very long time for me to figure out how to use this, and I don't even remember if I read it somewhere, if I could find an example, or if my teacher told me. This is an example of how to use it, because I wanted to have a given example if you want to use this. So what this actually does, you have two types of functions. One is a pixel function, you give it an image. Just forget about this for now. Okay. You have a pixel function, you give it an image and two coordinates, and it gives you a pixel. So you can define your own functions that give you a new pixel for a coordinate from an image. Basically, we're going to use this to produce a new image from an old one. And an image one is just taking this to the next level. You get an image and you get out another image. And the map image does this for you. You give it a pixel fun, and it applies it to an image and gives you back a new image that it created from there. So how does this work? You have this is a net alias. So the second parameter, you can call it image, or you can call by name the elements of the network. So you create a new vector, the size of which is that of the size of the vector inside the image you gave the function, and you create a new image using the constructor of this mutable image I showed you before. And then for all the pixels of the image, you write a pixel based on what this f function you gave it gives you back based on the image you gave it and the coordinates you're currently trying to map to a new image. And now after you've done this, using your custom function, you can freeze the image and get back another, your final image. And actually, this home fun is pretty fun, because you can give it a list of pixel functions, and it composes them in a way that you get back a regular image function. It's not that complicated. I'm going to explain. So you get a list, you map this map image function to all of those pixel fun images, the pixel fun functions. You get back a list of image to image functions, and then folder composes them. That's all. So now come the live example. So I'm gonna try to load what's called juicy.hs, and here in the source folder we have a spj.png with Simon Peyton Jones, and you run. I wrote a bunch of functions, and I'm just going to run them all using this. It is going to take a while, and while this runs, I'm tell you about that the GHCI, the interpreter for Haskell, is kind of slow when you do these kind of things. But actually, when this is over, I'm going to compile it and show you how much faster it is. So yes, it did it in 17 seconds. Well, let's see the results. It's Simon Bacon-Jones. It's him with pixel cores inverted. This is a core function. This is why it needs an actual image, so you can move the pixels around. If you just if you use a pixel to pixel function, you wouldn't do this. And this is both functions composed. So I think this is all. And this was kind of slow. Yeah, Haskell is not good for image processing. Yes, it is, because when you do this, you compile it. You can delete the image side. No, I did not. Going to now. It's already compiled, and I'm gonna just run qc.hmax. And it was a lot faster. Did it in 3 seconds. So yes, if you do some image sensitivities and huge long thing, you might have better luck with it if you compile it. Don't forget. There's a direct difference between the interpreter and the compiler. It's great. And here we come to our final example. Separating I and Q functions. So I set out to do this, which I've been trying to do for a while, which is to have a loop sort of thing, like a REPL, which stands for read, evaluate, print loop. You have a function, and you have a prompt, and you type something in, and the computer says something back, and evaluated or added something. So what happens here is that all you need to do is keep providing the function, a state-to-state function, and your state has to provide ways of setting an input on it and an output on it. So the state actually stores the input and the output, and the Boolean variable whether you should still run it. So it's just when it turns false, the loop quits. So you read get line to IO. But yes, this is a bit complicated. It's just the state T is a state transformer monad. It just takes a regular IO monad, and you can also do state things in it now. That's all it does. And it has the same state that you have to provide a function that works on state to state. It has to have the same state behind it. So you read something into I, and you modify it. I modify it to, no, actually at first I set the input on it with this function to I, and then I apply f to it, which is your custom function, and then I modify the state behind it to this new state, because it actually just changes that state. And then I read it back, because this actually changed, this actually already did whatever you want to do in F. It reads this new state back to ST, and then it gets the output. This get output is, you have to write this to on your for your state. You have to implement actually this kind of interface, this type test for your state. You just put it somewhere in your state, and you say how to get it out. So you get it out, and this loop prints it out. This I was just because it's a state transformer thing, don't worry about it. And then if it's still running, you have to be able to, your state has to be able to tell if it's still running. If it's still running, it calls replube F recursively. So actually, if you want to run all this, there is a function run replube F as eval state T. It's just T because it's a state transformer, and it runs this action, this monadic action, which is actually this function, and start a state. If you actually want to do anything in this, you just have to provide an interface for your custom state, a function which takes your state from to the next state, and call this with those two things, and it's gonna do whatever do the whole thing. So actually, if you see, you just have to do a function state to state, so you don't have to worry about in the IO monad. This is the separation that I did for it, and you can do like a text adventure with this or anything. I just did a simple example, which I am going to now present. So I don't know what it's called, sec. Yes, here's the example. This is all of it. So run example, yes. Run example. So now I already have prompt. All this does is if I say something, it gets angry and shouts it back at me. And if I tell it a name, like Bob, it remembers that name. So if I say, hi, Bob, it remembers it. If I say, hi, Alice, I don't know you. So you see, it has an internal state, and you give it input and it gives you back output, and you don't have to, you separate the IO from the logic of your code. And if I say exit, it quits. So this is actually, it's like 5 lines of code and some other things. But it's this simple to separate IO. It could be done more complicated, it could be done better with more versatility. But I just wanted to give a simple example. So that's all. I hope you enjoyed this presentation. And thank you all for listening, and thanks Gabor Bari who helped with this presentation. So yes, I think I'm done. And does anyone have any questions? Does anyone? Yes?
Could you show the code of the last example? Could you show the code of the last example? How does it look like when I can separate the function from the
Yes.
IO?
On the slide or the whole code?
On the whole code.
Yes. Now I'm gonna try to put this up somewhere so you can all look at it. So yes, this is the example. It doesn't actually fit the whole screen, but it almost fits. So it has these values. R is for whether it's running, R is for the output, I is for the string. You can change it or not. You can actually keep the same out and names. No, it's confused. Sorry. And names has all the names you gave it. So this is very simple. The example is it has a start state. It's also is running by default. It doesn't have anything around it, and it doesn't have any names. And it has these accessor functions for just setting and getting. Of course, it doesn't actually change the state of the original state. It just creates a new one. I think everyone who is familiar with Haskell knows that. Example fun. What does it? Yes, it's the function I give it to run, but it actually uses this longer parse function. So it run example, it's run example start. So it uses these things. Start states of the script, and anyway, parse does this. It's not very pretty. I was just kind of hurrying when I wrote this. It's just checks if it's exit or if it's not the prefix, and otherwise it just shouts it back next to buffer to it.
Okay, thank you.
Any other questions? If nobody else has a question, I have a question. Who feels that this presentation helped them understand monads a little bit more? Oh, thank God, I didn't waste all of our time.
Awesome. Thank you very much. Any other questions? No? Alright. Then thank you very much. Will you be here for questions? If anybody has any else?
Sure.
Alright.
Why not?
So then see you upstairs.